Welcome back, everybody, and you are in Mr. Smith's Honors Chem class. Now, last time we were talking about the universe. We said, hey, you know what? From a chemistry standpoint, the universe is really composed of two things. It is composed of energy, and it is composed of matter. And things that are electromagnetic in nature are energy, light, microwaves, radio waves. These things are all energy. And then we said the things that what really characterizes matter, and let's write down the definition here. The definition for matter is something that has mass and it has volume. It has stuff and it takes up space. Anything that has mass and volume is what we consider matter. Now, this time we want to get into more concepts related to matter, and specifically, we want to talk about the types of matter and how you can distinguish between them. All right, so let's take a look at our first consider for the day. There we go. A piece of copper and water, and 3 hydrogen atoms. Identify each of these as a pure substance or a mixture. Okay, so we want to find out what's a pure substance and what's a mixture, and then make a particulate drawing of each. Okay, so let's first go back and let's learn a little bit about our types of matter. So we know there are at least 2 types of matter, right? We just figured that out. There is something that is called a mixture, and there is something that is called a pure substance. And by now, you probably know with me that I really am a believer in definitions. If you can write down what something means, that means you probably know what it means. So here we go. Let's write down a definition of a mixture. So let's come over here. What is my definition of a mixture? Okay. Well, I'm going to say that a mixture is a blend of matter in which each component maintains its identity. Okay? So that is my definition of a mixture where each component maintains its identity. Now let's think about something like let's say we have some oxygen. Let's say we have a beaker here, and we have some oxygen. And oxygen is usually 2 atoms that are bonded together. And we'll say that we have some gold, and then so we have some gold in here. All right. And that's AU. So we have oxygen and gold. And what makes this a mixture? Well, I've got a blend. I've got oxygen and gold, but my oxygen stays oxygen and my gold stays gold. So if I were to separate this, my oxygen would still keep its identity and my gold would still keep its identity. So that's what makes a mixture, is that the components, oil and water, sand and water, carbon and steel, all of those things are blends, but each component maintains its identity. Okay, so now how is that different from a pure substance? So let's write down our definition of a pure substance. And the way I like to think about a pure substance is that it is matter with a fixed. And what does fixed mean? Unchanging, always the same, with a fixed composition. And I like to think of something like H2O. So we all know what H2O is, right? H2O is water. And if we were to look at H2, well, not really look at it, but one way we consider it is looking as an O, an oxygen, with a couple of hydrogens on it, almost like a Mickey Mouse, and that looks like a bear, right? And that's H2O. Now, let's say I have an oxygen with 3 hydrogens on it. Is that water? Well, no, it's not water, because water is always what? H2O. There are always 2 H's and 1 O. That composition of H2O is fixed, never changing. So that means water, H2O, is a pure substance. Now let's go back over here. Well, Mr. Smith, this looks like a fixed composition. Well, what if I put down 3 golds and had an oxygen? Would we still say this is a mixture of gold and oxygen? And the answer is yes. It is a mixture of gold and oxygen. Over here, I have 1 oxygen and 2 golds. Here, I have 1 oxygen and 1 oxygen compound element and 3 golds. So, the basic idea here is that this, in a mixture, it is not a fixed composition. Its composition can change, and so that's how we distinguish between them. All right? Good. Did we answer our question yet? Well, no, we need to what? Yeah, okay, good. So here we go. I have a piece of copper. Now, a piece of copper. Do we think that copper always has the same composition? And in all likelihood, if we said, we should probably say pure copper to let us know that there's no impurities in it. But so we'd have a piece of copper, and it's all copper. And it will just say we have 5 atoms of copper. Is that fixed? Is that unchanging? The answer to that is yes. So copper is going to be, copper is going to be a pure substance. How about a piece of copper and water? Well, so we could have some water in here. Let's draw some H2Os. And we have some copper down here at the bottom. Now, could I have 2 waters and copper? Yes. Could I have 3 waters and copper? Yes. Could I have 4 waters and copper? Yes. Would all those be known as a piece of copper and water? And the answer would be yes. So is this a fixed composition? The answer is no. This would be a mixture. Good. How about 3 atoms bonded to a nitrogen? So I have a nitrogen and 3 atoms of hydrogen bonded to that. All right, so my hydrogens are always smaller than my nitrogen. Now, can that change? Can I write this as 4 hydrogens and nitrogen? Would that still be ammonia? No. Excuse me. Yeah, ammonia. No, that's not ammonia. If it lost an electron, that would be ammonium. So this thing is always the same. It has a fixed composition. So my ammonia is a pure substance. Cool. Now, you can see I've started to draw already some things, and let me give you a couple of tips on this particulate drawing. What we mean by particulate is kind of on the molecular level. Now, if we look at something like copper, we know that copper has what? It has like 29 protons and 29 electrons. So I don't write 29 positives and 29 negatives. When I do a particulate drawing, all I really do is I draw a circle and I put the symbol inside. Now, when I draw a compound, so that's just an atom. Now, if I'm going to draw a compound like water, I represent water with a circle. And then when I overlap them, that means I am the overlap represents the overlapping of their electron clouds. And so that would represent a molecular bond, all right? So when I'm showing a molecule in which they're bonded, I show some kind of overlap, and that's really about it in terms of particulate drawings. Okay, so a piece of copper just has some copper atoms next to each other. And so that would be, and let's put these usually in a box or in a beaker. So that would represent our piece of copper. A piece of copper and water. Okay, so here we go. Here's how I'd represent my piece of copper and water. I've got to have some water in here, so let's draw a couple of them. Which always draw a couple, 2 or 3 molecules. So there's my oxygen and water, and you may not have enough space to put your H's in. That's okay once you do that. So let's draw a couple waters. All right, so there's some waters. There's the overlap. Good. And then let's draw a copper in here. Okay, so that's how I would draw a copper in water. Now, the important thing here is notice my copper is not overlapping on any of the waters, because if my copper overlap, that would indicate that there's a bond going on. So don't show the overlap. And then let's show a couple of our ammonias. Also, notice that my molecules don't overlap each other. So here's an ammonia in the middle, and we've got 3 hydrogens. And then let's draw another one in the middle. And you don't always have to put they can be turned around and things. It doesn't matter where the O's are, I mean the hydrogens are. Eventually we'll learn, but that's okay. But notice, I don't have these guys overlapping each other because my molecules are not overlapping, or else they become one big molecule. All right, good. There we go. Here you go. You guys do this one. You got 4 atoms of chlorine bonded to 1 atom of carbon. You have 5 atoms of antimony, and then 2 atoms of neon gas in a tube with 3 atoms of helium, and draw them. Bring me back when you're ready. Just pause and bring me back. Okay, here we go. 4 atoms of chlorine bonded to 1 atom of carbon. By the way, when you see that word bonded, that usually tells me what? Is it a fixed composition? Yes, that's going to be fixed composition. If it's a fixed composition, it is a pure substance. And how would I draw that? So let's come over here. Let's put these in a box. So how would I draw that? I have, a carbon. So let's put a carbon in here. So here's a carbon. And then I'm going to have to put 4 atoms of chlorine. Chlorines are pretty big, much bigger than carbon, but we'll learn that later. And I really didn't draw that one much bigger, so let's draw carbon smaller, and big old chlorines, big old chlorines, big old chlorines, big old chlorines overlapping. There you go. So these would be my chlorines, there would be my carbons, something like that would be your picture. Next, 5 atoms of antimony. So I have 5 atoms of antimony. By the way, antimony is Sb. So let's go with 5 atoms of antimony. Yoink, antimony. Yoink, antimony, yoink. They're not overlapping, they're not bonded, but they're just hanging out together. And so we'll put them in a line like this. And now, is that composition ever going to change? Am I going to have 6 antimony? Am I going to have 8 antimony? The answer is no. I'm always going to have 5 antimony. And there's nothing else listed, so it's only antimony. So is this fixed? The answer is yes. So my 5 atoms of antimony represent a pure substance. And then I've got 3 atoms, it's 2 atoms of neon gas, so I have a tube. Here's my tube. I have 2 atoms of neon gas, so let's put in neon, let's put in another neon. Now they're not bonded. And I have 3 heliums, and let's put a helium here, and a helium here, and a helium here. Now the question is that a fixed composition? Is that changing? Can I move that around in a different way? What if I did this? What if I put 1 neon here and 1 neon here? And then I put my heliums in between all in a row. So would you say that these two are, that this is fixed, that this is fixed? And the answer is, well, if I could do it this way, no, it's not fixed. So this would represent a mixture. And I'd accept either one of these as your particulate drawing. Great. Moving on. Next, okay, so let's consider water, copper, ammonia, manganese. Which of these are elements and which are compounds? All right, so let's go back up to our beautiful drawing, and let's talk further about my pure substances. Let's talk about, we know that they can be elements, and they can be compounds. So what's the first thing we know? If we want to start our definition, we know that they are pure substances. So this means it would be a pure substance. So it's a pure substance. And what else makes an element unique? It's a pure substance composed of atoms with the same number of protons. That's what an element is, composed of atoms with the same number of protons. And the number of protons defines what an element is, right? So why is carbon copper? Why is carbon carbon? It has 6 protons. If it had 7 protons, it's no longer carbon, it is now nitrogen. So everything that has 6 protons is carbon, right? So we're saying a pure substance is composed of atoms with the same number of protons. Got it. Another way to think about this is a pure substance which cannot be broken down. Now we're not stopping there. It can be broken down, but it cannot be broken down into a simpler, and here's the important word, stable substance. All right? So this is my preferred definition, but you might also see a pure substance which cannot be broken down into a simpler, stable substance. Now, in contrast to that, we have our compound. And one way to think of a compound, it is a pure substance. It's a pure substance in which atoms with different number of protons are bonded together. Or an alternative definition is what? Parallel to the one next to it. It's a pure substance which can be broken down into a simpler, stable entity, substance. And if we look at 2 examples, right, I could have iron. Now, is iron made up of atoms of the same proton? Yes, they all are Fe, right? Can this be broken down to a simpler, stable substance? Well, I could rip off a neutron, I can rip off a proton, I could rip off a electron, and the question is, does that still represent a stable substance? And the answer is essentially no, and so iron is an element. What about iron oxide? Iron 3 oxide, FeO. Okay, not FO, but Fe2O3. There we go. So what about iron 3 oxide? Well, can I break this down into ions and oxygens? And the answer would be yes. And are those stable? Well, if this were an O2, the answer would be yes. And so then you can break this down because it can be broken down like this. And so that represents a pure substance. Good. Let's go back to our question. Water. What do you think? Can I break it down into hydrogens and oxygens? Yes. So this would be a compound. Copper, can I break that down further? No, that's just an element. And the easy way too is if you memorize your elements, you know if it's not an element, it must be a compound. And manganese, element. There we go. So let's draw then 3 molecules of water. So over here, 3 molecules of water. What am I going to do? I'm going to have an oxygen, put a couple hydrogens on it, overlapping, oxygen, couple hydrogens on it, and oxygen, couple hydrogens on it. O, O, O. And the key here is you have the overlap, but yet each molecule is not overlapping. If we draw 3 atoms of manganese, you can draw them anywhere you want. You just do not have them overlapping. There we go. That's the way I would do that. All right. Here you go. You guys do this. Bring me back when you're ready. Sodium. What do you say? Sodium, piece of cake, right? Sodium is an element. Carbon dioxide, I've got carbons bonded to my oxygens. By the way, how would I draw carbon dioxide? Carbon. And the O2s are not together. They're on opposite sides of your carbon. So that's how carbon dioxide looks. So it's made up of two elements, OO and carbon, bonded together. So I would say that is a compound, right? Sure, that's a compound. And then CO, good. CO, once again, that is a what? Compound. This is easy stuff. Okay, so let's draw 3 molecules of carbon monoxide. So I have a carbon, and I have an oxygen, and they are kind of like this. And actually, that's a triple bond. You can't, it's hard to draw a triple bond like this right now, so we won't try to draw a triple bond. And let's draw another one like this. Yoink. So here's my carbon. Oops, that's beautiful. And here's my oxygen. There you go. So there are your 3 molecules of carbon monoxide. Make sure they show an overlap between the carbons and oxygens, but there is no overlap between the different molecules. Super. Moving on. All right, here we go. I have a fresh glass of Pepsi, some undissolved at the bottom of some water, some undissolved copper at the some copper undissolved. Okay, got it. And air well ventilated in the room. Super. Here we go. Homogeneous or heterogeneous mixture. So we need to go back to our questions. What's the difference between our types of mixtures? So we want to work off of mixtures up here. So let's come down, and we want to talk about the 2 types of mixtures that we're going to run into. And they are homogeneous and heterogeneous. Good. Those are our 2 types. Let's go with the definition. What is the definition of a homogeneous mixture? It is a mixture in which it is a mixture not with in which, but it is a mixture with a uniform. And what does uniform mean? Same throughout. A uniform composition. It's slightly different. Notice we're not saying it's unchanging, that it's fixed. We're just saying it's the same, right? Whereas a heterogeneous is a mixture without, WO, without a uniform composition. And the way I think about this is if I were to taste or drink this mixture, if I had something like sand and water, and I have sand down here, and I have water up here, and I were to drink from the top and drink from the bottom, would I get the same stuff? If I drink from the top here, what do I get? I get water. If I drink from the bottom, what do I get? I get sand. Are those the same? The answer is no, which means it is not a uniform composition, and sand and water would be heterogeneous. But if I had a little bit of sugar in some water and that sugar was completely dissolved, I wouldn't see the sugar at the bottom or at the top, and so I'd have some sugar at the top with some water and some sugar at the bottom with some water, and it would be real well mixed. And if I drank up here, I'd taste some sugar water, and if I drank down here, I'd taste some sugar water. So I'd say sugar completely dissolved in water is homogeneous. Okay, that's it. So let's go to our question. Let's knock out this set. So I have a fresh glass of Pepsi, right? So if I have Pepsi, what do I think? Do I have Pepsi? You have to understand is what? I've got some sugar in there, and I have some carbon dioxide, and I have some water, And if you have a good Pepsi, doesn't the first bit of Pepsi taste like the last bit of Pepsi? Meaning the sugar and carbon dioxide and water are all well mixed. And if it's all well mixed, that would mean it has a uniform distribution, and we'd say that this is homogeneous. How about some copper undissolved at the bottom of some water? So I have some copper sitting down here, and I have my water throughout. Does that look like it is uniform or non-uniform distribution? Well, uniform would have the copper spread out and the water spread out. Instead, I've kind of have the coppers at the bottom and the waters everywhere else. So I would say this is heterogeneous. And air in a well-ventilated room, well-ventilated means what? Well mixed. That means, air is primarily what? Oxygen and nitrogen. That's essentially what air is. You got some carbon dioxide maybe in there and maybe a little argon. But if it says it's well ventilated, that means it's mixed up real well, meaning up at the top, I should find some oxygen and some nitrogen and maybe a one argon. And at the bottom, I'm going to have the same kind of arrangement, but they're going to be really spread out. And no matter where you sample, you're going to get some of all three, right? And so we would say this is probably going to be homogeneous. Perfect. Super. All right. I think this is the last question. Yes. Okay. Last one of the day. You guys do it and bring me back when you're ready. All right. Carbon dioxide and water. Draw 3 molecules of carbon dioxide and water and four waters. Show me a heterogeneous. Okay, so we want to see a heterogeneous. So I'm going to draw a big picture here. If it's heterogeneous, it's going to be what? Not uniform throughout, meaning I'm going to put all of one thing in one place and all of the other thing in another. So maybe what I'll do is I'm going to put my carbon dioxides all over here. So here's a carbon, and here's a couple oxygens. Once again, I didn't have that right, did I? I need to have small carbon. Small carbon. No, that's right. I had it right. Oxygens are slightly smaller. But in any case, I'm going to put all my carbons and dioxides, all my oxygens over here. So there's my carbon dioxides, and I'm going to put all my waters over here. So here's a water, and here's a water, and here's a water, and here's a water. There we go. And notice that if I sample on this side, I'm only going to get water. If I sample on this side, I'm only going to get carbon dioxide. And so this would be a representation of a heterogeneous, homogeneous. What am I talking about? Homogeneous. No, heterogeneous. That's right. Sorry. Yoink, yoink, yoink. Heterogeneous. Good. And then what would be my homogeneous? Homogeneous would mean what? That it has a uniform composition. So that means I'm going to want to spread everything out. I'm going to want to have one carbon dioxide up here, and then maybe a water somewhere up here, and then maybe another carbon dioxide over here, and then another water over here, and then another carbon dioxide over here, and maybe a water over here, and I need another water somewhere. In any case, you want these all spread out so that all the carbon dioxides are not together and all your waters are not together. And so this would represent a uniform composition. And so we'd say that this is homogeneous. All right, great. Glad you're with me. Sorry to take so long. See you next time.